Welcome everyone. My name is David Kamm and I'm a first-year PhD candidate at Sorbonne Université, and my PhD topic is reducing uncertainty in climate models through improved parameterizations of small-scale processes. And since we're quite a mixed group and I don't know everyone's background, I want to give a small introduction into why we need to improve parameterizations. And I like this figure here by Hewitt et al. From 2020 because it really summarizes the problems. So what you see there is the different, like all these dots are the different ensemble members of the CMIP6 simulations. And on the y-axis, you see two different matrices. So in the top panel, that's the AMOC strength, so the Atlantic meridional overturning circulation strength. And in the lower panel, it's the ACC, the Antarctic circumpolar current. And so that's the y-axis. And then the x-axis for both plots is the respective horizontal resolution of these ensemble members. And what you can, and also this gray bar that is not so well visible is what we know from observations. And what this shows immediately is the majority of these ensemble members is very coarse. So the average is 58 kilometers. So the majority of them needs to parameterize the mesoscale. And it is also known and also visible here that this introduces biases into the results of the climate model. So you can see it quite nicely for the AMOC, that the coarse resolution runs with 100 kilometer horizontal resolution have a weak AMOC, while the high resolution runs, they have a higher AMOC that is well in line with the observations. And yeah, one consequence of this could be, okay, let's just increase resolution, but this is first of all quite costly and also only solves part of the problem. If you look for the ACC, for example, increasing horizontal resolution does not help you with the bias there. So there's even smaller scale processes that you need to resolve. And bottom line of this is, okay, we need to improve parameterizations, and we will still need to in the future. And there's also a lot of work ongoing to tackle these tasks. And I wanted to quickly highlight, quite randomly, these three papers where they try to tackle this problem with machine learning. So they try to replace or improve parameterizations with machine learning techniques. But they sort of tackle quite idealized issues. So they are very promising parameterizations, but it's very hard to bring them into climate models. And this is sort of where I see myself. So I'm trying to run an also idealized but semi-idealized configuration that you can see here. The name is Dino, a diabatic Neverwall-2. And Neverwall-2, that is a configuration that was proposed by Marquez et al. In 2022. And so I sort of had the idea to bring this into the NEMO framework in Paris to test parameterizations. And so both configurations, Dino and Neverwall-2, are a closed Atlantic basin with a periodic Southern Ocean channel. And they have an idealized bathymetry where you see here the mid-Atlantic ridge and here the Scotia arc. And Dino, in contrast to Neverwall-2, has a diabatic primitive equation model behind. And in Marquez et al., it's a stacked shallow water model. And the benefits of these configurations are that they're cheap to run while keeping the key properties of the dynamics of the model. So you can run them on very high resolution while still maintaining things like an AMOC, an ACC, Gyre systems, and metrics that we care about in climate models. And this is why I think it's a great configuration to serve as a test protocol for novel subgrid parameterizations. So a very quick run into how the circulation looks like in Dino as is right now. So on the left-hand side, you can see the barotropic stream function, giving you a broad sense of the horizontal structure of the circulation. And you see the expected gyre systems, subtropical, subpolar gyres, even a Weddell-Sea gyre. However, you also see that the ACC, the circumpolar current here in the bottom, is way too weak with 70 Sverdrup compared to 170 from observations. And when you look at the meridional overturning circulation, we see here in the top two tropical cells that we also would expect. We see a upper branch of the meridional overturning circulation that is also slightly too weak, but also within the range what we saw from the CMIP6 simulations. What is missing is we don't have a deep cell that is connecting to the Southern Ocean. And so this is currently not in the configuration, and we're sort of balancing if we want to continue working on this to get it perfect, or if we accept the not so perfect configuration. And then in the last step, I also wanted to highlight that Dino serves as a model hierarchy. So it's not just a configuration that is run at one horizontal resolution, but at several. So similar to Marquez et al., we want to run the simulation at 1/32 degrees horizontal resolution. And in order to do this, one technique we employ is to do the spin-up, the expensive spin-up of the model at a coarse resolution. Then we cut the velocities to 0 and interpolate the temperature, salinity, and SSH fields to high resolution and continue the run. So as you see here from Marquez et al., and then they reach very, very high resolution. And we tested the same for Dino, and just as a proof of concept, it works quite well. So, which I'm quite happy about, because I wasn't sure if this would work as well in a diabatic model, but it's quite essential because like this we can reach a ground truth state, so a very, very high resolution state where we can expect that all the features that we care about, like the sub-mesoscale features, are resolved, and we can use that to test any parameterization, but also to train machine learning-based parameterizations. And also another goal is, since we have another project ongoing in Paris, which is called semi-automatic tuning, which I won't go into detail, but you also need this ground truth state. So yeah, I think I'm already at the end of my time, so I leave you here with questions.